basically want to talk a bit about modeling complexity in policymaking. It is largely based on a paper that I think got shared with you, which is about how to actually bring computational methods in the study of policymaking processes. And maybe just before we start, like why should we actually talk about policymaking? Why is it any important? So when I say policymaking, I mean the process of producing policies within governments, international organizations, the European Union, and etc. And in fact, it's actually more than $20 trillion a year that is allocated to different policies, to solving different challenges. In a sense, the entire global population is subject to policymaking because the global population is subject to a legal system in different countries. And there are future challenges such as potential wars, future pathogens like COVID or others, or technological developments that will actually pose challenges in the future and which are dependent on how we deal with them at a policy level. But when we think about policymaking, we can think of policymaking as a social network and of different individuals that interact to agree on what needs to be done in the world, what kind of policies need to be implemented. And the question is, how can we actually coordinate such large networks of hundreds, if not thousands of individuals? And this is essentially like a scientific challenge, but also a practical problem. It is a scientific challenge to understand the complexity of a social network and how people manage to agree or disagree on different issues. But it is also then like a practical problem, because if we know something about policymaking processes, how can we actually improve global coordination, collective decision-making processes, and etc. And my presentation tries to tackle a bit like these two challenges using complexity theory and computational modeling. But I would like to ask maybe like an uncommon question, which is, what do conflicts and policymaking actually have in common? I know that some of you in the room are interested in conflict. Ravi definitely is. But what do we know about conflict? We know many things about conflict. We know that it's also subject to social network dynamics. But conflict is essentially about outright killing each other, while policymaking is essentially trying to agree and coordinating. So why do these two things might actually share common properties? So we know something about conflict, that the distribution of conflicts according to their frequency and severity actually follows a power law. That has been measured in 1948 already by Richardson, and that has been further validated 70 years later by Closet and others. This essentially means that a few wars or a few conflicts account for most of the casualties generated by conflicts worldwide and over time, which means that the distribution basically has a long tail in the end, where like very rare events are extremely severe. So this is something we know about conflict, which is a statistical features that seem to be valid over time. What is interesting is that you actually have the same distribution when it comes to policy changes. You also find a power law. So this is the distribution of policy changes in the US on the right. At the top, it's the distribution, and then at the bottom, it's the log-log plot. So it's just a different way to represent the power law. And then you can see that basically you have a long tail, which means that you have a few changes that account for most policy changes in budgets. So this basically means that when people in governments decide to change policies, usually it doesn't happen very often. And when it happens, what happens is only like very few changes over time and very small changes over time. And only very rarely you have very large changes that occur and that account for most changes in public budgets. This is the data in the US. This is the same distributions that we observe in the UK, in Denmark, in Canada, in Belgium. All of the countries actually depict power laws. This is the French distribution and the German distribution. also power laws. This is the distribution in Hungary compared to the normal distribution, also a power law. So you may think that like it's just for government, but in fact, it also applies to the EU, to the UN as well. You might think that it's only for Western government, but in fact, it also applies to China. And then you might think that it's just for the government as a whole or for organizations as a whole, but in fact, it also applies to policy subsystems. So these are 5 different subsystems of the Defense Department in the US, and each of the subsystems also depict power laws in policy change. So what we know is that there are like statistical signatures at a system level. So we see power laws. Essentially, a few conflicts generate most casualties, and then a few policy changes account for most budget changes. This is something that we measured over time, which is pretty well validated. And the question is, but what are the underlying mechanisms? Like what explain the fact that we have these like non-normal distributions of changes at a macro level? And if we ask this, maybe we can ask, can we actually model such mechanisms and replicate the statistical signatures? And if we can, then we might actually be able to explain something at the micro level and what actually produce these laws at a system level. And fortunately, this has been done in conflict studies. This is a very recent paper where they modeled the dynamics of conflict avalanches in Africa. And you can see that the blue line is essentially what the empirical data reflect. And the orange curve is what the computation model actually produce. And you can see that it's actually pretty well validated between the empirical data and the simulated data. The problem is that here we don't talk about conflict, we talk about policymaking. And in policymaking, this type of modeling has been extremely scarce. There's no history of modeling like you have in conflict, of like decades of people that have been trying to model conflict. In policymaking, this is very scarce. Complexity theory is actually mostly used in a way that is very theoretical. So the question is, how can we get to the same plots or like the same kind of research, but in policy studies? So the goal of my presentation is the following. First, sorry, I won't actually present any successful attempts to model policymaking, but I will present how to actually get there. So I'll focus on applying complexity theory to policymaking and then maneuvering the step from theory to formalization. And then I'll discuss what we can do scientifically and practically if we actually manage to create these empirically valid models of complexity in policymaking. So this is basically based on the paper I shared with you called Computational Policy Process Studies that I wrote with some colleagues at the Simon Institute. The outline of my talk is the following. I'll briefly talk about studying policymaking processes, what they are and what's the current state of the art. I'll talk about complexity of policymaking, what the current theory says and how it's studied. I present a very simple verbal model of policymaking and then a mathematical version of it. And then I'll briefly reflect on the utility of modeling that complexity and what we can do with it. So first, what is policymaking? I briefly described this already, but essentially, we know that like there's a world in which we implement policies, and these policies, whether they are regulations or redistributions or general like soft power created by international organizations, come from policymaking processes in which you have analysis, you have vested interests, you have emotions, you have different opinions that actually are blended and then used to produce these policies. And this process essentially happens within governments, the EU, the UN, and etc. And when I mean policymaking, it's really about this part, which is covered by policy process studies in the literature, and which we should not be confused with policy analysis, which tries to analyze the interplays between policies and the world and whether policies are actually effective or they're not effective, how much they cost, whether they're appropriate or not. And here we're not going to focus on policy analysis, but actually on the social processes of policymaking. So this is a quote which gives a good definition of policymaking, and we're going to use it a bit later in the presentation. So essentially, policy processes consist of politically engaged individuals called policy actors interacting to influence government decisions in relation to a topical issue of the time. Policy actors come from various organizational affiliations. They include politicians and public officials, managers of public and private companies, members of pressure groups, academics and researchers, and active citizens. And finally, policy processes do not occur in a vacuum, but within the institutional system of a country or a subunit of a country, as might be found in federal forms of government. So this gives a view of policymaking that is not a black box with some input and some output, but is actually an inherently social process of actors that are actually interacting and sharing their opinion and influencing each other. In terms of methodological developments, a lot of the research in the space is very theoretical, where researchers try to develop theories of the policy process. So this is a diagram of one of the main theories, which is the advocacy coalition framework. So essentially how different coalitions co-evolve and then manage to converge to agree on a policy. There are a lot of qualitative research. So for example, on studying narratives and how they spread in policy systems. Narratives are really important because they define essentially what people care about, the worldviews that are actually spread in policy networks. And then a lot of the research conducts interviews with policy actors to understand how they think and whether like narratives propagate or not in systems. There's a lot of quantitative work. At the top, you see the power law distributions that I just showed, which is one of the key programs in policy process studies. And then there are also other quantitative work on trying to understand beliefs and like who people believe and etc. And this is mostly used using regression analysis and etc. And then there's a lot of work using systematic reviews to review concepts, to try to assess what the state of the art in the discipline is, and etc. But in fact, what we see here is that like the system level explanations of like what explains social dynamics is mostly at the theoretical level or at the qualitative level. The other quantitative analysis rather try to get some like statistical relationships between independent variables and dependent variables, but those analyses are more like black boxes that do not tell us much about the inner workings of policymaking. And then I want to delve into the complexity of policymaking because there is actually a very wide scholarship using complexity theory to address policymaking. Very briefly, I know that you've covered this in other parts of the course. What are complex systems? I think the most stripped down version is that it's a network of adaptive agents whose interactions shape and are shaped by system level properties. This can be seen in policymaking, but in conflict, in migration, in economics, in studying the climate, in studying chemistry, physics, biology. And this is essentially like a general theory that we can adapt to study specific systems. So how does this theory actually apply to policymaking? Here's the definition we just saw. So we can highlight a few points. The definition basically emphasizes that we have individuals interacting, which means that we have individuals in networks that share connections and that influence each other. Individuals have different affiliations, so we have heterogeneity of individuals. And then we know that this network of heterogeneous individuals actually is not within a vacuum, but within an institutional system. So there's a surrounding environment that produce incentives for people to behave in a certain way, to believe different things and not others. And over the past maybe 2 to 3 decades, there has been a theoretical convergence in policy process theories. There's like an implicit convergence. So there are at least 5 theories that actually use concepts of complexity theory, but without referring to complexity theory and to complex systems, but they essentially use the same. So the advocacy coalition framework talks about bounded rational agents and the co-evolution of coalitions. Multiple stream analysis, among others, describe how actors react to exogenous events. Feedback theory formalizes the effect of policy output on policy processes. So like basically how like system level outcomes influence micro level processes. Policy learning mostly describe the adaptation of individuals and groups, so like adaptive behavior. Then punctuated equilibrium theory produces the power laws essentially, and then describe that those power laws are a function of bounded rational agents that have a limited attention and that change their attention as a function of exogenous events. And then there's like explicit use of complexity theory, where essentially people map the properties of complex systems on the properties of policymaking systems and basically claim that complexity theory lends itself well in the study of policymaking processes. But where the convergence is that all of these bodies of literature actually agree that policymaking consists of adaptive bounded rational agents that interact in a social network, and that this interaction leads to the emergence of nonlinear emergent dynamics, such as these power laws. And all of these theories basically subscribe to this view, implicitly or explicitly, but which basically shows that currently in policymaking processes, complexity is actually widely accepted and widely used. And then the question is, what to do next? Where is the frontier in studying complexity? So the current methods to analyze complexity is mostly theoretical. So it's mostly about like building a narrative on how to think about policymaking processes. There are like a few scholars that have been developing computational models. I think in total, there are only 15 of these models. But these models have been barely successful, either because they are either overly simplistic or overly complicated, or they're too detached from the literature. So then they do not resonate at all with the literature and with the scholars that have been developing the theories. And then there's a third line of research, which consists of the opinion dynamics from physics, which are also fairly detached from the literature, and those models are actually mostly mathematical and not computational. So a current frontier in analyzing policymaking, complexity in policymaking, is to essentially build these empirically validated computational models, where the idea would be to model adaptive agents in networks, so like formalize these micro level processes to then replicate the emergent dynamics that we already measured using data. Basically the power laws I showed you before. That could be other macro level dynamics like patterns of opinions. And then the idea would be to seed the micro level processes with data. So for example, data on network structures, on policy beliefs, on the number of agents in the system, and etc. And then the idea would be to validate the macro level dynamics with data. So for example, data on policy budgets, data on opinion patterns, and etc. So here's just a quick overview of building computational models, such that we're all on the same page. This is adapted from a chapter published last year by Ravi and others. So first, the idea is to like conceptualize a model based on theory, based on interviews, based on data, and then to move to model implementation. So to formalize the conceptual model and to implement it as a software in a computer. Then the idea is to do data construction. So it's to collect data at the micro level and at the macro level and prepare it to seed and validate the model. Once we've done that, we can move to model validation and refinement and to assess whether the model we actually built is well calibrated and actually replicates the empirical data that we see in reality. And if we manage to do this, then we can run counterfactual analysis to evaluate some critical points in the system when, for example, like a system shifts from one state to another. And for example, in the example of power laws, when does a big policy change occur that then accounts for many changes in public budgets. So this is like the process of computational modeling that you might know, maybe it's taught in this class. And the paper that we wrote essentially tries to go from step 1 to step 2. We don't try to go further away because what we think is that currently in the literature, the bottleneck is to go from model conceptualization to model implementation. It seems that there's a lack of mathematical and computational education in the field that prevent the people that subscribe to complexity theory to actually build computational models of these systems. And then as a result, they essentially describe complex policymaking systems at length in books, but they don't necessarily describe these systems as explanatory formal models. So we try to facilitate this process essentially with the paper we wrote. So here's a minimal verbal model of policymaking. The idea here is to have like one of the most stripped down version of a policymaking system such that we can model it. And if we've managed to model it, then we can extend the model. So the minimum model is policy actors have 2 adaptive characteristics, which is their current attention and opinion. They interact within a decentralized network structure, and they update their attention and opinion as a function of their neighbors' characteristics. Actors pursue 2 strategies, trying to reach better positions in the network and forming coalitions with value-aligned actors. And then iteratively, this process leads to aggregate patterns of attention, such as periods of inertia and periods of change, and then the contagion of opinion. So the assumptions in here, first is that it's agent-based. Here we talk about actors that interact. We don't necessarily talk about the abstraction of actors, like in a group or in an institution. We actually disaggregate the system to individuals. The agents are adaptive, so they actually change over time as a reaction to what others think and what the environment actually says. Agents have only 2 characteristics, which is the attention, which is what they care about at time t. So whether they think about poverty or climate change or about COVID or about something else. And then the second characteristic is opinion. So it's what they think about what they care about. So whether they are anti-vaccine, anti-mask, or pro-vaccine or pro-mask, whether they are pro-policies to cut CO2 emissions or not, and etc. Actors have 2 actions. One is to reach better position in the network, so try to improve like the connections they have. And then the other one is to build coalitions with value-aligned actors. These agents interact in a decentralized network topology. So there's not just like one single actor that is very central, but you have different clusters. The agents adapt the behavior as a function of 2 things. So what the neighbors actually think. And then it also adapts the action as a function of where they are in the network. And the least central they are in the network, then the more central they will want to become, essentially. And then from this, we would expect to see periods of inertia, so where the actors essentially focus on different problems, everybody looks into different directions. And then we would see periods of change where actors actually align their attention. And then we would see periods of contagion where similar opinions actually spread in networks. Is this overly simplistic? I would believe that in many political science departments, many scholars would say, oh yeah, but you forget many things. What about emotions? What about narratives? What about the environment? Yes, all of this is actually left out. But the point here is not to be entirely realistic. The point is to have the most simple model in order to know whether we can actually model it and then on which we can add extensions. This model actually is very well substantiated because there are at least 5 theories plus complexity theory that validates its premises. So the fact that agents are bounded rational and that they have this adaptive attention is actually widely discussed in most theories. And then the minimal model is actually already complex, because here we talk about agents that have two characteristics that update their mind as a function of the network. And the network is also changing as a function of people's action in this network. And that in turn leads who shapes which opinion and etc. And that can already lead to some complex dynamics at a system level. So what is a mathematical version of this? And here, I do not want to present like a final model that works, but the point here is more to explain how we can go from this verbal model, which might seem correct or might seem interesting to study, to something that is actually formalized that we can implement in a computer model. So I will present 3 steps. The first one is to formalize agents states. The second one is to formalize policy networks. And the third one is to formalize agents adaptive behavior. So first, formalizing agent states. So each agent is essentially defined by an internal state vector, which we use to store information about each agent. And this vector is divided into 3 subvectors. So like one opinion vector, where each opinion is included within the range between 0 and 1. And it's essentially characterized by a float. And then there's a second vector, which is the exact same vector as the opinion vector, but it's the attention vector, where essentially here you would have a vector that says what people focus on. And then depending on what they focus on, there's a second vector, the opinion vector, that says what they think about what they focus on, essentially. And then there's a third subvector, which is the strategy vector, and I will describe this later. And then these 3 vectors essentially consist of the main agent vector that depict the actor characteristics, or like the agent states. And this essentially formalizes who the agents are. That's essentially it. Second, formalizing policy networks. So we decided to propose like a stochastic matrix to formalize policy networks. So essentially a stochastic matrix is this. So it's a matrix with n rows and n columns, where n is the number of agents. And then each number in the matrix specify whether the agents are connected to one another and what is the weight of their connection. So for example, in the policy network, you might have people that know each other very well and that trust each other, and some people that just loosely know each other. And that can mean trust, that can mean alignment, or other things. So the network consists of the relationships between the agents. The connection strength here, we actually decided to put it as a function of alignment. So as a function of the extent to which people agree on their attention and on their opinion. And then it's an adaptive network, which means that the matrix can be rewired over time. And I will describe how this happens in a bit. And then third step, we actually model the evolution of the social network as a multi-layered co-evolving network. And I will describe what this means. So here's essentially the network topology at t+1. So at the next time step. So let's say tomorrow. So essentially the network topology is like which agents are connected to which agents, and then to what extent, and what's the weight of connections. And this is the actor states, so what people focus on and what their opinion is. So the network topology and the actor states are essentially a function of the network topology and the actor state at the previous time step. And it's a function that is an update function, which we need to specify. And here, what is important to understand is that like by just specifying this way, we already capture a lot of the core of complex system dynamics, which is essentially that you have a network topology that changes as a function of what people think and of the network topology previously. And then you have the state of the actors that change as a function of the network and what people think. And this over time is basically like a recursive loop that can create this nonlinear dynamics. The question then is, how does all of this update? And that's about specifying the function f. And then here we actually specify function f in two ways. So first is through like a function h, which the agents will try to minimize, which is essentially the function that will define how people update their opinion and their attention. And they try to minimize it because they try to basically match what the other agents next to them think, which can then reflect concepts like belief homophily or opinion contagion, the fact that you have filter bubbles where like everybody thinks the same. This is what this function essentially captures. And what we add in this function h is a stochastic component to account for cognitive limitation. Because as you remember, the theories say that we have bounded rational agents, meaning that we don't have fully rational agents. They don't have full information, and they cannot fully understand what others think. So there will be errors in the update, and then sometimes they will over-update, sometimes they will under-update, or sometimes they will wrongly guess what others think, and they will try to imitate them, but in a wrong way. And that's what this stochastic component actually accounts for. And then as a result, what this just does is that it formalizes the update of attention and opinion as a function of external cues and the strength of network connections. So essentially, agents will update their mind as a function of other agents think, which is a pretty common social phenomenon. And they will also weight their update as a function of the strength of the network connection, which means that they will update their mind more strongly if they know someone very well, and which actually makes sense. If a friend tells me something, I'm more likely to actually update my mind than if it's a random stranger that actually tells me the same thing. And that's what basically this formalization tries to capture. And then we further specify the function f by formalizing the agent's actions. So here we have two actions, as I said. And these actions actually only capture the preferential attachment mechanism, which is essentially what kind of connections in the network agents try to have. So there are two actions. One is to increase actor degree centrality, which is how many connections they have, and they try to have more connections than the others. And the other action is to form correlations with value and goal-aligned agents. And what here is about is that we create a maximization function where actors try to maximize two things. So they try to maximize the utility related to action 1, and they try to maximize the utility related to action 2. And then depending on this utility, basically they decide to pursue the action to a larger extent or not. And then that basically will give the entire utility, which each agent tries to maximize because they want to maximize their position in the network. And that's essentially what just this maximization optimization function captures. So in summary, what we just covered here is maybe very mathematical for some of you, maybe overly simplistic for some of you. But what we can see is that we have a simple model using just a vector of agent states, a stochastic matrix to model social networks, a multi-layered co-evolving network logic to define how the network topology and the actor states actually change over time. And then to specify how these two things change over time, we have a minimizing function where actors try to imitate what their neighbors actually think, and then a maximize function where actors try to maximize their position in their network. And what all of this does essentially is that it captures bounded rational attention and opinion dynamics. So we have actors that change what they think about and what they think about what they think about, essentially, but in a way that is messy, that is based on limited information, and that can be very random. We have adaptive networks, and there's also strategic behavior because we will have agents trying to pass the network and try to find better positions in it. There's a key limitation in this, is that the model is actually Markovian, which means that the model doesn't remember history. Here, if you remember this multi-layered co-evolving network equation that I showed, it only specifies the evolution of the network based on the previous time step, which means that actors actually do not remember what happened previously. They just remember what was at the past time step, but not before, which might be a limitation because in politics, you might have conflicts that actually last over time and that prevent people from agreeing from like longer time frames. But being Markovian might actually be a good approximation of reality. This is something that still needs to be validated, but it's an assumption that needs to be explicit and acknowledged when we do the modeling, essentially. Once we have all of this, we can essentially explore some key questions. One is, how does the system steady state depend on its initial configuration? So if we have more or less agents, does that change anything? Then we can ask, how sensitive is it to the actor's rationality or randomness? So I described this like stochastic element that will basically specify how much errors actors actually make when they try to guess what others think. And we can actually minimize this stochastic component and make people very rational or very irrational and see whether like the structure or the dynamics of the system actually change as a function of this individual component. We can assess the rate of convergence and how it depends on the dimensionality of opinions or the capacity of attention. So for example, we can complexify like the opinion structures by having opinion and sub-opinions. So like, for example, one might think that we need to cut CO2 emissions, but one might think about this for different reasons. And then we can further spell out this. And this will increase complexity and might affect whether people actually converge towards similar opinions. Question we can ask is, do we already observe punctuated equilibria? So do we observe this sudden changes that account for most policy change without external shocks? That would be an open question. And then if we don't have any, maybe we want to add shocks to see whether it makes a difference. And then we can ask whether like there are some strategy profiles that correspond to groups that actually we observe in reality, so, such as policy entrepreneurs. So we know that policy entrepreneurs are usually very well-networked individuals that are really good at convincing others about changing their opinion and their attention. Can we actually observe this type of agents in the system? Does it correspond to different network positions, so different strategies? This is something we can essentially explore. Once we have the simple model, we can build extensions. So we can add additional actor states. So here, for example, the actors do not have different affiliations or different characteristics, for example, like a political party. And what we can further specify is also like some cognitive bounds. So we can specify maybe core beliefs. So in our current model, people can basically shift their opinion and their attention very freely. But in reality, some people have some deep core beliefs. So like they would not update their mind entirely, they might update their mind slightly. And we can ground this with core beliefs and restrict the amount of update people can make. We can add exogenous events that might refocus the entire attention space. We can complexify the opinion space, like the problem space, for allowing for ambiguity, which is one of the big problems in policy, which is essentially that a problem like climate change or COVID is very ambiguous because different actors have different definitions of this problem. This is something that we can use if we use a multidimensional problem space. And then we can add a learning component where actors will try to improve the strategy profile as a function of their performance over time. And then there are some other extensions we can include in further modeling efforts, essentially. So lastly, what is the utility of doing all of this? You might ask, we have the theories, they already explained quite a lot. We have the power laws. like, what's the added value of doing this modeling? And it is like a reasonable question to ask, because it's quite costly to build these models, and it's not always certain what we can actually get from them. So I think one key thing that we can get from this is to reconcile micro and macro dynamics, which is a key scientific challenge, especially in social sciences. We know in the literature in behavioral public policy, we know a lot about individual behavior and a little bit about group behavior. So the fact that people use biases and heuristics in the face of uncertainty, that they have limited information. But that doesn't tell us much about other things at the system level. In policy process studies, we try to describe these networks of individuals and how these networks change as a function of the behavior of bounded rational agents, which already try to put together more like macro or meso considerations with micro level processes. And then we have comparative policy studies that try to assess, among others, these power laws across context. But these power laws, or like the statistical analysis, doesn't tell us much about the dynamics of networks or the dynamics of behavior. And here, what we try to do in the modeling I just showed is to reconcile these three elements, among others, where essentially we model bounded rational agents, we model networks, and we try to replicate these macro level dynamics. And I think this is the power of complexity science, because instead of dividing the field into different streams of literature to analyze different parts of the system, we try to actually put them together to explain something that seems very important, because policy change seems to be a function of individuals and networks, and we need to find ways to explain this. And there's a practical problem that we can address with these models, is that the improvements that we sometimes talk about when we want to reform policymaking systems, or we want to improve policymaking dynamics, such as changing voting mechanisms, changing the structure of party systems, spreading decision norms, for example, having a decision-making culture that is inclusive or that is reasonable, or maybe introducing participatory procedures, or maybe even like information provision. So like in evidence-based policymaking, we supply evidence to policy networks. Essentially, all of these improvements, or all of these interventions, they happen within policy networks. They do not happen in a black box, so they do not directly affect policy change. It affects policy change by actually changing the dynamics of policy networks. And that basically raises the question of how to intervene in these networks, and how to intervene effectively, and where to intervene. And this is basically related to the question of like, what are systemic leverage points? And if we only take policymaking as a black box, which is usually the case in policy analysis, where we only study policy outputs, then we have very limited understanding of what it means to like make a network more decentralized, more centralized, to spread a norm, to improve people's reasoning, and etc. While these are the dynamics that actually generate policy change or not. So I think this is like a practical problem that is also at the core of the Simon Institute that I didn't present, but this is a little bit of the things we try to think about. And arguably with computational models, we can get closer to this type of understanding, and potentially then closer to improving policymaking processes in a pretty rigorous and empirical manner. So overall, what I think all of this means is that we know that the theory on policymaking processes converge toward using complexity theory either implicitly or explicitly, but there is a current frontier in studying policymaking complexity, which is the use of formal methods and computational methods in a way that is anchored in theory and in the literature and in data. And essentially, this is what we propose in this paper, to try to like advocate for this computational turn in policy process studies, and to show how to model like a stripped down version of policymaking processes to then motivate people to continue to do that and push the field further, essentially. Yeah, that's all from my side. I'm happy to talk about all of this, receive feedback, and discuss your questions or other reflections on complexity science. Thank you very much.